My pleasure to introduce Yehuda Lindell. He is the head of cryptography at Coinbase and was a CEO at Unbound Security. He's also a professor at Bar-Ilan University, and he's going to talk today about Exponent-VRFs and their applications.
Thank you very much. So this is joint work with Boneh and Iftach Haitner. The work really came out of looking at a number of different things that we wanted to do, and then just observing that it turns out that all of these things, and actually many other things, can all be derived from a single, very, very simple primitive. Simple in the sense that very simple to describe. How simple it is to construct, that I guess the future will see. But my aim in this talk is to convince you that this is a very interesting primitive, and you should work on finding a simple and efficient construction of it, and then we get all of this beautiful stuff for free. Okay, so what's a verifiable random function? I think everybody knows this by now, but I'll go through it. It's a pseudorandom function with an additional proof that I'm computing the correct value. So in order for this to make sense, I have some sort of commitment to my secret key or a verification key, which is some sort of commitment to that key. And then I'm proving when I provide a value that this is actually correct relative to that key. So now we're sure that every time that I compute the pseudorandom function, I'm actually giving you the correct value according to the key that I committed to initially. That's all a verifiable random function is. So what's an exponent-VRF or an eVRF? It's exactly the same thing, except that instead of giving you the output of the pseudorandom function, I'm going to give you the output of the pseudorandom function in the exponent. Okay? That's the only difference. So depending if you like additive or multiplicative notation, I see everybody here goes with multiplicative, so you're going to swear at me throughout this presentation because I've been doing additive for the last, I don't know how many years. I am a traitor to my field. So in other words, instead of giving you just y, I'm going to give you y times g in elliptic curve notation or g to the y in finite field notation. That's the only difference. So it's extremely simple to understand what this thing is. Right? This is not a complicated primitive. It doesn't have a complicated definition. There are some small additional details, like you want a simulator that can extract the private key during the generation of the verification key, but that you can pretty much imagine is not very difficult to do. Some sort of zero-knowledge proof of knowledge, and it's only during the generation phase. Okay, so very simple primitive, but it turns out you can do lots and lots and lots and lots of stuff. In general, the idea of the intuition is that there are many cases when we're trying to do protocols for threshold signing, threshold cryptography, or other things where we need to generate a random scalar, multiply it by the generator point, and send the result. And if we need to make sure that we're proving correctness or other properties we'll see later on, then with an eVRF, it's sort of atomic, because the eVRF automatically gives you this. You don't have to do a separate operation and prove consistency or anything like that. That's the basic idea. But so what? And so here are all of the applications that we have for this very, very simple primitive. The first is the two-round, fully simulatable multi-party Schnorr signing. The fully simulatable part is the novel part here, and I'll spend probably about a quarter of this talk talking about simulation-based definitions and why I'm in favor of them and why I prefer them. And part of the reason is because I'm really old, I know that, but I think that actually they have significant advantages and we should consider them. The second is a two-round, fully simulatable two-party ECDSA signing protocol. And I conjecture that we can do multi-party as well, but I haven't done the work, and I'm assuming that something like with Abi's protocol, we could plug it in and do that. Two-round, fully simulatable deterministic multi-party Schnorr. Not perfect on the threshold part, but without the threshold for sure. One-round, fully simulatable distributed key generation. You need some sort of unique nonce or timestamp for that, but in practice, that's absolutely fine for key generation. MPC-friendly HD derivation like BIP32, but MPC-friendly that I can also verify that I'm doing the correct thing. And when I get to that later on in the talk, I'll explain why that's important, why it's not trivial. Something called a proof of quorum identity for multi-party Schnorr. Now it's after the protocol, the set of parties who have signed can come and prove that they are the ones that signed. Think about, for example, you're giving a reward to people who actually signed. They can come and claim that reward, and they can't, and nobody else can cheat. And all of the protocols are usually secure, meaning that they're secure under general concurrent composition, and they're secure for any number of corruptions. And our constructions are all using standard assumptions in the random oracle model. So this is like a long list of all different things that we get, and these things are not generally not known, or some of them you can do, or maybe all of them you can do with very generic MPC methods, which are extremely expensive and have a cost which is relative to the size of the circuit computing what you want to do. A circuit computing exponentiation is infeasible, not infeasible, it's close to infeasible in practice. So all of these are actually new constructions and things that we couldn't do beforehand, and all of it just with this very, very simple primitive called an exponent-VRF. Okay, so now you can go to sleep, because as long as I've convinced you that it's an interesting primitive and it's worthwhile researching, it's going to do all of these things for free, I've done my job, and I can leave, and we can finish right now. But because they gave me an hour, I'm now going to drive you nuts. Okay, so I want to spend a while talking about simulatability, because I think it is important, and I want to discuss the difference between simulation-based definitions and game-based definitions, and what we can gain, what we gain if we can achieve a simulation-based definition. And it is harder typically to do, but in many cases we can get it. Okay, so what's a game-based definition? A game-based definition, we have a very specific task. It might be signing, it might be decryption, but it could also be many, many other things. And we design a specific game that expresses the security that we want for this specific task. Okay, so we have an adversary who can interact with oracles that participate in the signing, and then they have to output a signature on some message which hasn't been agreed to sign. This is the standard type of definition if you go back to the non-interactive protocol world. When you're defining signatures, you're defining encryption. This is essentially a game-based definition where we set up a game where I have to try and distinguish between encryptions or things like that. For encryption specifically, it turns out that that's actually equivalent to semantic security, which is actually simulation-based definition. In simulation-based definition, we do something very, very different. Think about an imaginable ideal world with a trusted party who will compute the function, whatever function it is that we want to compute for the parties. And then we're going to compare our real protocol to this ideal execution. So this ideal execution, the parties send their inputs, get back outputs, and that's it. And we want the output distributions to be indistinguishable, or essentially the same. And so for threshold signatures, you would just define a trusted party that would, for example, get key shares and then sign on the message or something to that effect. And because in the ideal world, the adversary can't do anything, then likewise in the real world, that's what we get. One of the rationales for using simulation-based definitions is that a very simple and clear ideal functionality is a very convincing security definition. So if I have a simple ideal functionality which says, parties give me key shares, I verify that they're correct relative to the public key that they also sent me, I sign on the message and send back the signature, then this is very, very convincing. I understand exactly what I'm getting. Over the last decades, ideal functionalities sometimes are no longer very simple. You can see ideal functionalities themselves, which are half a page to a page, and they enable the adversary to interact because there are some things that otherwise are very complicated. If it's simple, still simple, and it's easy to understand, that's fine. When ideal functionalities start becoming very, very long, then part of the justification for why we want this type of definition, maybe we're losing a little bit. But the original motivation was that we want to have something where we don't need to work hard to define security each time. And now it might seem that, okay, we understand our definitions very, very well, but actually definitions take time to be understood. And we have definitions of encryption and signatures and other things in the beginning looked fine and actually needed to be refined. And if you have like an ideal model-based definition, then it's very, very simple. But there are other advantages as well, but that's just one thing I wanted to point out. Okay, so going a little bit more in detail, the idea of the ideal model is that this is the best you could possibly hope for or to achieve. So you have an incorruptible trusted party, doesn't exist in the real world, but this is the ideal world. many things we can do in an ideal world. We can have world peace even in an ideal world. All the parties have ideal private and authenticated channels between themselves and this trusted party. So they'll send their inputs to the trusted party over these perfect channels so nobody can interrupt or eavesdrop. The trusted party computes the output correctly because they are trusted and incorruptible, and sends each party their output back, and that's the ideal world. So in other words, what can an adversary do in the ideal world? They can choose their input. That's all. By the way, that's important. Sometimes being able to choose your input freely as whatever you want can be significant to security, but that's the only thing the adversary can do here. And not only that, their input that they choose, they can only choose before they've seen any output. They can't see some part of the output and then choose their input. That's the only thing they can do in this ideal model. So this ideal world is fantastic, and we can clearly see that if each party holds a shamir sharing of, for example, of a private key, and all they do is send it to the trusted party who reconstructs, compares it to the public key and signs, that this protocol will reveal nothing about the signing key, and forging a signature in this model will be the same as forging a signature, a standalone signature. Okay, so the ideal model actually just computes the functionality in the same way, or the signature in the same way that a standalone signature signer would. And this goes with the philosophy that what does MPC in general do, and threshold signing is a specific example of MPC. What MPC says doesn't say anything about the security of the function. Right? If you're doing MPC to compare DNA, and output some properties of DNA compared between two people, MPC doesn't tell you anything about what that reveals about you, right? You can do secure MPC, for example, for two people to compare their salaries or to output the average of their salaries. You can do that. You can use MPC to compute the average of two people's salaries. It's a really dumb thing to do because given my salary and the average of two salaries, I know the other person's salary, right? MPC doesn't say anything about if the function reveals anything. What it tells you is that the process of computing the function reveals nothing. So if my trusted party, if my ideal functionality computes the signing algorithm like a standalone signer, that means that the fact that we're using this potentially complex interactive protocol with people sending messages, it just looks exactly like as if I had a standalone signer in a secure box. Okay, this is also, by the way, one of the things that using MPC, if you've already built it, is actually quite easy for engineers, because what you tell them is you want to design a secure system that does something. Here is this ideal box that computes this thing. So just pretend that you have this secure box, this secure hardware that does this thing, and now you can use that to build your system. The fact that you're actually not using any secure box, and the fact that this is an interactive protocol with parties holding different shares in different parts of the world makes no difference whatsoever. Okay, so that's the paradigm of the ideal real model. And then we say that a real protocol is secure, and this is of course not a definition, it's an intuition, but if it behaves like an ideal world execution, or stated differently, the secure computation, the protocol will emulate this incorruptible trusted party. Formally, we say for every adversary in the real model, corrupting a certain number of parties, there exists an ideal world adversary who we call a simulator, but that ideal world adversary is just corrupting the same parties and working in the ideal model and interacting with the trusted party. But the output distribution of both the honest parties and the adversary in the real world and the ideal world is essentially the same. So if in the ideal model, the only thing the adversary can do is choose their input, then also in the real world, that's all they can do. And as long as that doesn't make any difference to us, then everything is fine. So this is the definition, the simulation-based definition. Why? What are the advantages of using a simulation-based definition? I mentioned one beforehand, that if I define the ideal functionality very cleanly and easily, then I have high confidence that it's doing what I want, whereas game-based definitions can become complex because their complexity grows with the complexity of what I'm doing. Okay, that doesn't mean you can't have a good game-based definition. Of course you can, and we have many very good game-based definitions. But if you look at, for example, the game-based definitions around password protocols, they're much more complicated than an ideal functionality for a password protocol. Okay, much, much more complicated. And there are many more things you need to take into account. And that's true in many other things as well. But that's one advantage. The second advantage, and this is one of the most significant, or if not the most significant, is composition. When we use UC security, and it's important I've seen people make this mistake, simulation-based definitions is not the same as UC security. Right? We have also simulation-based definitions for standalone protocols, which implies sequential composition. But with UC security or universal composability, it's a specific definition which is simulation-based. Then we have the guarantee that the protocol remains secure no matter what other protocols are running together concurrently with that protocol. And with game-based security, you do not have such guarantees. I mean, it depends on your game-based security, but your game-based security definition can and should take concurrent composition into account, but it can only take into account concurrent composition of that protocol, or something called concurrent self-composition. So if I'm running this signing protocol many, many times, then we want to make sure you can't forge a signature, even if you can concurrently interact in multiple protocols at the same time and try to steal messages from one to the other, or do whatever you want. I can give you that guarantee. And good game-based definitions for threshold signing will certainly take concurrent composition into account. However, what happens with other protocols? Do I have a guarantee that running this protocol over TLS channels, or next to I'm running a Schnorr protocol next to a different ECDSA protocol, can I say that everything is fine? Maybe that other protocol will somehow ruin this protocol. So in general, you cannot say anything. When you're thinking about threshold signing, you can say something, but it's a little bit weird. And I don't really know I don't myself really fully understand what exactly is going on here, but I'll try to go through the thought process with you. So let's think about a world where everybody has all keys are fully independent. What that means is that my ECDSA signing key is just a random key and not dependent on anything else in the world. And if I'm running an ECDSA protocol and a Schnorr protocol, then my keys for that are truly random, completely independent keys. In that case, what I would argue is the following thing. Okay, so let's assume that running this ECDSA protocol or other things together with this Schnorr protocol somehow ruins it. If that's the case, since all the keys are independent, then now I'm going to play a game where I choose all the other keys in the world, except for this one key, and now I'm running them all concurrently. But what is it concurrently? Everything else I'm just running internally because there is no other protocol. And at the end, if I can break Schnorr, then now I can break Schnorr when it's just Schnorr and nothing else. So I can make that argument. But can I say something about the simultaneous security of ECDSA and Schnorr? Not really. I mean, I can say that I can simulate the whole ECDSA world and the Schnorr will be fine. And I can say I can simulate the entire Schnorr world and the ECDSA will be fine. But can I say, so I couldn't forge a signature, but could I say something about, can something strange which is correlated between them happen? I don't know. I can't really claim something about simultaneous security across them all. I don't really know if it matters, but if there are fully independent keys, I can say something here, but it's not all there. That's all I can say. It's a little bit weird, and I don't really know exactly what we can say. Maybe it's interesting for someone to do that and go through that process and say what we can actually say in such situations. But with UC security, I don't care. And even if I'm using dependent keys, it's fine. What UC security tells me is it doesn't matter what else you're doing. And even if the keys, I'm using the same key for Schnorr and ECDSA, which is you're not allowed to do that, right? Then what I'll do is I'll get the same level of security as if I use the same key for ECDSA and Schnorr that I did standalone. So the fact that I'm coming back to the previous slide, the fact that I'm doing an interactive protocol makes no difference. Just think about the security as if I had standalone executions.
Going back to the concurrency issue, if you just have a game-based definition and a security proof, it's not clear that you can handle an adversary that nests a bunch of sessions, right?
No, your game-based definition has to take that into account. So any game-based definition that respects itself will consider a concurrent game. And even if you go back to the game-based definitions of Rogaway and for key exchange, who was it? It's Phil and someone else. And me here. Even the definitions in the early 2000s that did this, They were concurrent definitions. They had these oracles for the different executions, and you could call each oracle and each execution at a different instance, and these were stateful oracles. So concurrency being built into game-based definitions is not a new thing. Not a new thing at all. But it's absolutely essential, yeah.
The objection to composing game-based security is that it's weird, which is I think that's fair. But I'm curious if you have real examples.
No, it's not that it's weird. I'm saying that you can formally argue concurrent self-composition within itself, but once you're adding other things, then you don't have anything formal really you can say. You could formally argue that my Schnorr signature is fine, as long as it's an independent key, of course. And I can separately argue that my ECDSA signature is fine, but I can't really argue them simultaneously. Does that matter or not? I don't know. But certainly formally, I can't say really what I want to say. In the next slide now, when I talk, or in a slide later, when you don't have fully independent keys, then I can say very, very concrete things. That's what I want. That's what I want to get to. In terms of the reduction in a simulation-based definition, and okay, here I'm sort of lying a little bit because it depends on your game-based definition, on your simulation-based definition. There are two flavors. One flavor, which is the one that I personally prefer, is where the ideal functionality, the trusted party, computes the signature scheme. So it computes Schnorr or it computes ECDSA. There are simulation-based definitions, which is what Ran Kennedy does and Nikos also does, where the signing functionality doesn't compute Schnorr. It computes some ideal signature, which is you give me a message and I give you a random or an arbitrary string, unique string, and say that's your signature or something to that effect. I'm not talking about that flavor. I'm talking about the flavor where I actually just compute the ECDSA signature or just compute the Schnorr signature. In that case, I don't care if ECDSA is secure or not. And in fact, in my job, I really don't care if ECDSA is secure. Because Bitcoin chose to use ECDSA, and that's Bitcoin's problem. They didn't ask me. It's not my responsibility. What's my responsibility? My responsibility is that the protocol that I use to compute that signature won't make it any worse. Right? It won't break things. It'll only make things better. It'll now make it that I have the benefits of protecting the keys and threshold approval and all those sort of things. So when in a simulation-based definition, I'm reducing to the actual signature itself, because that's what the trusted party is computing. In a game-based definition, I want to stress, depending on how the proof works, you may be reducing either to the signature scheme, but you can also be reducing to the underlying hard problem and not the signature scheme itself. And there is a difference, with that. Okay? And again, it depends. If you just see the game-based definition, you don't actually know. You'd have to go and have a look at the proof. With ECDSA, this is a very big problem because we cannot prove that ECDSA is secure. So the proof should really reduce to ECDSA, and there are certainly proofs like that, that's what you do because you can't prove ECDSA is secure. With Schnorr, you actually have to redo forking lemmas and all those sort of things, and there is a price to be paid for that in terms of complexity. There's a price to be paid for that in terms of the tightness of reduction sometimes. And also there's a very slight, I would say it's an epsilon advantage, an infinitesimal epsilon advantage, where maybe Schnorr is secure, but the actual assumption or being used is not, which is not, it doesn't make any sense actually. But you can talk about those sort of things as well. But this is a difference between them.
I'm not sure if I fully agree with this weaker. Except for the composability.
This is very minor. This is more about a difference than it is.
Right, but I understand what you're saying. Oh, you're gonna. I'm thinking about my paper where we showed that even if you bias the key distribution, you can still Schnorr is still fine because. But at that point, the forking lemma and all of that is already there, right? Because if I'm assuming Schnorr, the forking lemma and all of that complexity is already there. What's the problem to bring it back into the reduction of the protocol? In a simulation-based definition, you're saying the protocol is fine and all that complexity is in the proof of the underlying primitive.
I do think there is a difference between assuming that Schnorr is secure and proving my protocol secure under discrete log with a complex forking lemma. Because firstly, these are complex and subtle, and you can get them wrong. But second, the question is, why do you think Schnorr is secure? Do you think Schnorr is secure because discrete log and random oracle? Or do you think it's secure because it's been around for so many years that it's secure? Personally, I think that ECDA is secure because it's been around for so long. Not because of strange proofs that in generic group models that don't really match well with ECDSA. That don't convince me at all. I think that at some point when a primitive has been around for so long, that the primitive itself, we have a certain confidence in it, which is somewhat independent of a proof which has some idealized models possibly inside it. Maybe yes, maybe no. With Schnorr, I agree with you, it's much more minor. With things like ECDSA, it's more significant. But this is where it's really, really important, and I think the biggest reason why we should look at composition. The other things really pale in comparison. So with independent keys, I said it should be okay because I can simulate everything except for this. But what about in the real world, are keys truly independent? Okay? So what happens if I have a mnemonic? I have 16 words that I use for my key, but I have an ECDSA key and a Schnorr key and a BLS key. So I have 10 words that are the same and 6 different words for each. What about my proof of security now? With a game-based definition, I have no guarantee whatsoever. I cannot say anything at all about security. With a simulation-based definition, I can say that it's as secure as if you did that with local computation. So if you took a BLS signature and a Schnorr signature and an ECDS signature with an overlapping mnemonic, bad idea, by the way, but if you did it, it's the same as what happens in my interactive protocol. Okay, what happens if I use a related password to derive keys? Or even make it simpler, even another related password. I use Yehuda 53 exclamation mark for my password to derive a key for ECDSA. That's all I do. Is that secure? I don't know, it's a bit weird, right? I mean, I'm hashing it, so I'm guessing that maybe I could say something like it relates to the entropy, or we can't say anything really about the security of ECDSA for this, or for Schnorr. You can't. And your forking lemma or serial will completely fail if I did that. What I can say is that my MPC protocol, my threshold signing protocol, for that key will have the same security as if you use the local computation.
In this related key scenario, do you also have to redefine your ideal functionality to have this?
No, I don't need to, because universal composability does it for me for free.
I'm not fully understanding. So let's say we take extreme examples. We're running a Schnorr signature, and we're running an ideal functionality of Schnorr, and then a different protocol. We're just revealing the secret key.
Yeah, so that it will be the same. The fact that I'm using the protocol, if instead of using an interactive protocol for Schnorr, you used a local signing, it would be the same. So if you have somewhere else which is revealing it, then it's going to break that as well. But the interactiveness of the protocol is not harming you in any way whatsoever. That's what I can guarantee. So that's a very, very big advantage, because in real life, most blockchain keys are not independent. If you're using HD keys, if you're using BIP derivation, they're not independent. They're not independent for hard derivations if you're going from parent to child in the tree, and they're not independent for normal derivations. So that means that you would actually need to have your game-based definition include what's happening with BIP32 or a different derivation method. You would have to take it into account in order to have in order for the security to carry across. But that becomes very, very difficult to do. And if you have a simulation-based definition, then it's for free. Whatever security I get, normal derivation is what people are doing. Then if I'm doing normal derivation, then I get the same guarantees. This is a very, very, very big advantage, because in the real world, keys are not truly random. People can use passwords to derive keys. In the real world, keys are related because we're doing BIP derivation, and many, many other things happen. And when I have a simulation-based definition, then I'm covered in the sense that you chose to use a bad key. Okay, I'm just not making it any worse. Whatever you have, that is, you maintain that same level of security, and the fact you're using MPC is only going to improve things. Okay, again, doesn't mean that game-based definitions are bad, and there are some cases where we can't get simulation-based definitions, and we have advantages or for efficiency and other things in game-based definitions, and we can get other things. It just means that there are significant advantages to simulation, and I think that if you can get it, then this is something which is preferable. Having done all of that, now let's get back to the topic at hand. So we have a set of parties, and they want to generate a key. I want to do it in one round. So one round sounds very challenging, and I'll go through and see what the problems are, because if you get this, then all the other applications are sort of obvious. Okay, so what's the aim? The aim is for each party to get a random KI, which is their random secret key, a secret share of the secret key, and capital K, which is the public key, which is the sum of all the little KIs times G. That's the aim. That's my aim in distributed key generation. There are different variants for different protocols, but let's just take this basic variant. Here's a really bad solution. A really bad solution is everybody chooses their own KI, computes KI times G, and sends it out. Why is this really, really bad? Because a corrupted PN can wait to see everybody else's shares, or capital KIs, can choose a secret key that actually knows K and capital K, which is K times G, and then can just compute Kn to be K minus all the other parties' public shares. And then if you do that, what happens is the result of this protocol will be capital K, where Pn knows the entire private key. Okay? Is that problem clear? So I'm actually able to learn the entire private key if I do this type of key generation. So I can't just send out something, but if I want one round, how can I prevent this type of thing where I can fully determine the private key? So an attempt to fix this bad solution is to say that I'll make each party provide a zero-knowledge proof of knowledge of the discrete log of what they send. Why does that solve the problem? It solves the problem because Pn set Kn to be something which is K minus all of this stuff, and Pn could not know the discrete log of Kn. So once I force Pn to add a zero-knowledge proof of knowledge, I now solve that problem, and you can't do this attack. But a corrupted Pn can still wait to see everybody else's public shares and can now choose multiple little Kns so that the sum of them all, the capital K, has some property. For example, the third byte is all zeros. Now, Rosario says that I can prove that Schnorr is okay even if you can do that sort of thing. But you certainly couldn't do that with ECDSA, because you can't even prove that ECDSA is secure at all. So you certainly can't claim that ECDSA remains secure if the third byte, well, maybe the third byte is all zeros because the probability is 1 over 2 to the 56. But you can, but you can't claim that it's the same as the original signature. And most important, it's not simulatable. So if I want the advantages of simulatability that I said, then for simulation to work, it means I need to get a capital K from the ideal functionality, and the result has to be that K. So ideal functionality chose a random little k, computed a capital K, which is K times G. I have to make the output look exactly like that. Otherwise, I don't have any of the guarantees of simulation that I mentioned beforehand. So once I'm able to bias, then I can't do this. So what's the solution? The solution generally is to commit and open. So I commit to my KI, and then I open, and as long as the commitments are non-malleable, so I can't make my commitment depend on somebody else's commitment, this guarantees independence between them, and then we can claim that, that you're unable to bias the output, but it's still actually not simulatable, because to get simulatability, I need to be able to extract from each corrupted party their share that they're using. In order to understand that, let's look at what the ideal functionality will do. It would allow the corrupted parties to choose their own random input, their own random shares, or arbitrary shares actually, and would then choose the honest party's shares at random and then output the sum of the result. That's what the ideal functionality would do. You could, by the way, define ideal functionality where the trusted party chooses the random shares for every party. You can do that. That will be much more complicated to achieve and doesn't give you any security advantage. So the trusted party gets the inputs from the corrupted parties, and then chooses the random inputs for the honest parties. That means I have to be able to extract the honest parties' inputs, and in order to simulate that, I have to be able to extract, and therefore I just add to the commitments also zero-knowledge proofs of knowledge that I can extract from, and then I'm done. Okay, so that's one approach to generally get distributed key generation, and the simulator. This is, by the way, coin tossing, or what we used to call augmented coin tossing. It's exactly the same thing. So really stuff that goes back many, many years. So how would you simulate? You receive the adversary's commitments and the zero-knowledge proofs of knowledge. You can extract from the commitment, excusing an extractable and equivocal commitment. So I extract the values and I extract the secret values. I send to the trusted party. The trusted party sends me the capital K. And then I just choose random capital K, J values for the honest parties so that everything sums up nicely. And I open and I equivocate the commitments to be to those values and give simulated zero-knowledge proof. So I just lie about the honest party's values. But what's important here, as you can see in the simulation process, I need to have the adversary be fixed or be committed to their values before the honest parties provide theirs, which is intuitive because that's exactly what prevents biasing the output. But in the real world, it's the opposite, because we're assuming a rushing adversary, and the adversary can see the honest party's values first. So how do we bypass that? By using commitments that we can open and extract from, and so on and so forth.
So one mistake I've seen many times in simulation-based multi-party proofs is around extracting from NISX. So I guess, like, in looking at this, you're assuming that NISX are extractable in a multi-party case.
No, I said ZK POC, zero knowledge proof of knowledge. It has to be a non-extracted zero knowledge proof of knowledge. You can't extract if it's not a proof of knowledge.
Okay.
So if you're taking a Sigma protocol and you want it to be concurrently secured, it is the Fischlin transformer, not Fiat Shamir. If you do Fiat Shamir, you'll get a simulation-based proof, but for standalone or sequential composition, not for concurrent composition.
But there is, I think, one situation where if the adversary outputs all the Sigma protocol proofs at once, then we can still extract from many instances. I've seen it in this Shoup and Boneh book where if the adversary does Sigma protocol one after another and we need to extract one at a time, that is problematic, that they say. But if the adversary outputs all the Sigma protocol proofs at once, then they say that it's extractable.
Yeah, but I think it's probably going to be what we call, again, self-composition. Maybe they have a specific proof for when you're doing that. What happens if now I'm running this with other protocols where possibly you have related values? Then again, I think you'll have trouble proving that.
I see. So in the full simulatability, that will probably.
So that's why we use Fischlin transform, and the Fischlin transform, we have a paper about it now online. You can take a look, and the cost is very, very small. Like the proof of a discrete log is less than half a millisecond. So it's not significant. Okay, so what's important here is that in this way, the simulator is able to cause the output of the result to be exactly the key, the public key that I got from the trusted party, and that's why we get the simulation. So I'm able to bias the output to be whatever I want as a simulator, not as the adversary, and that whatever I want is what I got from the trusted party, and that guarantees that it's uniformly distributed and has the correct distribution. Okay, how can we do it in a single round? It seems impossible to do in a single round because in a single round, the adversary will always see what the honest party sent beforehand. So if the adversary always sees what the honest party sent first, the adversary can always bias their output. So how can it be possible to do this in one round? And the answer is only if the adversary has no choice over what value they're going to give, and if the simulator even knows ahead of time before the protocol starts what value the adversary is going to give. And how can we achieve that? Simple. Use an eVRF. How does that help? In the initialization phase, we're going to do one initialization phase, and then afterwards we can generate as many keys as we want with just one round for each key. In the initialization phase, each party just chooses an eVRF key. Here I'm adding a tilde to the eVRF key to distinguish it from the DKG keys. And then what happens is, given a nonce, and I said we need a nonce or a timestamp, because you need something to distinguish this execution from another execution, otherwise clearly it's impossible. So I'm given a nonce or the current time, and each party will just compute the eVRF on that value. and we'll send the capital Ki, which is the result of the eVRF computation together with the proof, and then you'll also add it all together. Why is this simulatable? The reason is that the simulator knows these Ki tilde values because it extracted them from initialization phase, and therefore it can just compute each Ki of the corrupted parties before the protocol even begins, and can send that to the trusted party and get back the capital K from the trusted party. Because the simulator already knows the Ki values of the corrupted parties, it can just choose the Kj values of the honest randomly, like we said beforehand, can lie about them being the correct eVRF values for the honest parties by cheating in the zero-knowledge proof as part of the eVRF definition, and then we'll just send those and we're done, and the output is going to be the correct output. So we bypass this problem with the adversary being able to bias the output by making sure that the adversary is committed to what they are going to output ahead of time. They have no freedom of choice. So they can't wait to see what the honest parties send and then do something different. Is that clear?
So you're also assuming the eVRF keys are extractable?
Choosing the which?
The VRF keys?
Yeah, I wrote that in the initial definition. I had another bullet there where I said, and you can extract the private key during the initialization.
And you add a proof of knowledge for that?
Mm-hmm.
I think you're pushing one round to the initialization, but this
but
is
you
very
initialization
generic.
once, and now you can generate millions of keys, each one using only one round. So what about threshold DKG? You can also do it. The idea here is to just do the same thing, but to generate each coefficient of the polynomial using the eVRF, and then you can get like type of Feldman VSS for a polynomial and add it together and do DKG. What about two-round simulatable signatures? And now everything becomes much easier because it's all just the same thing over and over and over and over again. Okay? So what are Schnorr signatures? We have a public key X, a public key Q, which is X times G. You choose a random nonce K. I know that K and X reverse here, but everybody gets mad at me for doing this. But my belief about notations is as follows. If someone's using notations which I really, really can't stand and I think are really horrible, then I'll change them. But if everybody's used to certain notations, I don't like to change it. So if you look at Wikipedia or in all these other sources about how people write ECDSA, for some reason, K is the nonce. And capital R is the result of computing K times G. That's the way people write it, so I sort of keep writing it. And now probably in 10 years' time, people will say, yeah, I hate the notation, but Yehuda write it that way, it's ready, so I'm just going to leave it. And this way we perpetuate terrible notation. So I choose a nonce K, I write R is K times G, and I output K plus the hash of the stuff times X. That's the signature. So how does the Schnorr signing protocol work? Well, we generate shares of the private key in some way. We generate a nonce in a shared method as well, where each party somehow, we generate these Ki values. And then it's just a linear function, which is why Schnorr is nice, because once we have that, I have my share of K, the Ki, I have my share of X, the Xi, and I can just add them together, and then I can just compute my local equation, and we can just add them all together. Okay, so that's Schnorr signatures. And as Chelsea mentioned, the challenge here, or the interesting part, is really this step here. How do we generate this nonce in a way that will be as we want it to be? And as I'm sure you can already see, in order to achieve simulation, what that means is I need to get a signature from the trusted party and make the output of the result be that signature. That signature includes, either explicitly or implicitly, the capital R. Okay, with the nonce, the public nonce, so R equals K times G. So I need to make sure that this step here, where we're somehow generating this nonce, the result of this will be what I got from the trusted party. Well, I'm sure you can all see this is exactly the same problem as DKG, so we can do exactly the same thing and solve it in that way. So how is the nonce generated? If I do a single round protocol, using other methods where parties send their nonces and we somehow combine them in a way with certain tweaks, like in some two-round protocols, then I can prove that this is a secure signature scheme, but it will not be Schnorr. It will not have the same distribution as Schnorr. It won't have the composability guarantees because I'm not able to make it actually be the same R that I'm getting from the external trusted party. In 2 rounds, I can generate it using commit and open, but then I get a 3-round protocol. So to get a 2-round protocol, I can just use the eVRF, and I do exactly the same idea as in the DKG. So I can simulate to get the R, and now I only have 2 rounds. That makes sense? And here it's not, the eVRF is generated during key generation, so there's no hidden additional round or anything like that. In key generation, we generate the eVRF key as well, and in each signing protocol, we have only 2 rounds.
In the 1-round thing, you use a simulation extractable NIZK for that first message?
For the...
It can't just be like a simple Schnorr.
No, because in the initialization, I've extracted the private key of the the private keys of the corrupted party. So I'm able to, I don't need to extract, I can compute it myself ahead of time. So during eVRF evaluation, I only need, if I'm using a zero-knowledge proof, it only needs to be sound. I only need a proof of knowledge during the initialization phase, so therefore I could use, if I had a Sigma protocol or something like that, I would only need soundness, I could use Fiat Shamir. Okay, so why is 2-round signing important? Not necessarily important, to be honest. But I think it's even an interesting type of feasibility result. Well, I don't know, feasibility result might be pushing things. Certainly 2-round protocols for Schnorr and for ECDs, or this is Schnorr, in the past were all not simulatable, but you do have these papers which are using generic techniques can do 2-round MPC, but they all work with the circuit. So I could state this as a feasibility result, the first protocol for 2-round simulatable signing with communication that is smaller than the circuit size. But I think it's interesting. I think it's interesting that you can do this, and it goes down to understanding of what we need for simulatability. There is a place where 2-round signing does make sense, and this is your question yesterday, Abi, and that's if you have a cold element. Let's say you have 5 parties, 4 of them online, and 1 cold element that you have to go into a room and do a computation. Then you have the 4 parties compute the first message. You can take them all, walk into the room, plug it into the cold machine. They will then compute their first and second round message. Then I go out and I can give it to the others, and they can finish the protocol. So that is a place where 2-round can make a difference if that is a model that people are using. Whatever deterministic signatures, well, what I showed you is actually deterministic as well, because the input that we use to eVRF for signing is the message. And if we use the message, if we use the nonce as well, then we can get probabilistic. But if we just use the message as the input to the eVRF, I'll now have deterministic signing because, again, I'm forced to use that message. There is no other message that I can use. There's no other nonce share that I can use. And then this enables you to prove security and show that you have deterministic signatures as well. And the cost of this protocol will be comparable to the cost of the eVRF. So if the eVRF is very efficient, and this is efficient, and the eVRF constructions we have, I'm not sure how much I'll show later, are reasonably efficient. So we think in back of the envelope estimates between 5 and 20 milliseconds. Threshold signing. So for threshold signing, it's a little bit challenging because the way I presented eVRF, it's a local primitive that each party has their own eVRF. So I have different sets of parties that are going to now be signing, they're going to be generating different nonces. So you can do this by including the set of parties signing into the eVRF. This will be secure, it won't be deterministic. If I want to get deterministic signing, I'm going to need to construct a threshold variant of an eVRF, something which we did not do. Okay, what additional results do we have? Notice that in this protocol that I showed you for multiparty Schnorr, the parties who signed also actually can generate a proof that they're the ones who signed because the eVRF computation has a proof that this is what the nonce is made up of. So if that's of interest. We can also do 2-round ECDSA signing, which is simulatable, and that's certainly something which is even more significant than Schnorr, because 2-round ECDSA, even game-based, we don't have under standard definitions, because standard assumptions, because you would need to reduce to the problem that ECDSA uses, but we have no proof of security for ECDSA. So ECDSA 2-round we don't even have for game-based definitions under standard assumptions. So, but here exactly the same thing. You can take a Lindell 17 and you can plug in the same idea for generating the nonce and you get a 2-round protocol as well. BIP derivation, this is the way BIP derivation looks. It's this tree and you can use, and it's based on HMAC SHA. But we can do this using the eVRF instead in order to do the derivation of each step. What are the advantages of this? Firstly, the public key is verifiable. So if I'm giving you a key, which I'm deriving in BIP32, you know that it's derived correctly. Why is that important? Let's think about a case where we want to do key derivation in MPC. Then I want to make sure that it's truly being derived from the correct private key. Why? Because I'm backing up the private key once, and I want to know that all of the keys I derive are secure, are going to be backed up because I've backed up that single key. But in a malicious environment, an adversarial party can just lie about the way they're deriving the key. It will look indistinguishable to you, and now what will happen is you won't have any backup for all of your funds. So we want to make sure that you can't do that, and you can solve that in an MPC-friendly way using an eVRF as well, in exactly the same way, because it's just a pseudorandom function, which is how you're deriving. So how can we construct eVRFs? Assume we have an encryption scheme which has a bunch of nice properties. Okay, basically a random ciphertext is a good ciphertext, it has a good distribution, you can prove properties that are efficiently about ciphertexts. Then we can do the following thing. You can create a key pair for the encryption scheme, and then give it an input. It's going to be the random oracle of the construction. Given input X, I will hash using the random oracle from the input to the ciphertext space. So now I get a random ciphertext. I will now decrypt that ciphertext to get some value Y. And then I will compute Y, capital Y equals Y times G, and generate a proof that the decryption, or what's inside that ciphertext, is the discrete log of capital Y. So can we do this efficiently? With Paillier, we actually can. With Paillier, you can certainly hash to a random ciphertext. You can decrypt. The space is not ZQ, the order of the group, but we can fix that without too much difficulty. And you can efficiently prove that a ciphertext encrypts the discrete log of a given value because of the homomorphic properties of Paillier. That proof is actually quite efficient. Okay? So this is not lightning fast. It's like tens of milliseconds, but you can do this. Yes, Abi?
Can you just go back one slide? What was the last proof you need to make? So you decrypt h of x. That gives you y. You compute y, and then you prove that the hash of x, which is the ciphertext,
it encrypts the discrete log of y. It's the same proof in Lindell 17 in key generation. You're proving that I'm encrypting the correct value. Okay, what about using DDH? We can do this with DDH as well. And the idea here is to use the PRF, the well-known PRF, which is just h is a random oracle going from strings into the group, and just k times h of x is a pseudorandom function based on the DDH assumption. It's also a VRF because you can prove efficiently that the result is a Diffie-Hellman tuple, and then everything is fine. But the problem is that for this output here, or capital Y here, is actually the little y we were talking about beforehand. We want to give that times g. We want to give the exponent of that. Okay, so here we can define a source group and a target group, and we want the order of the field for the target group to be the order of the source group. So basically we want to generate an element in the source group, and the x value would actually be of the order of the target group. So that's the way that we can take the output of this PRF and use that as the scalar for the target group, which is what we're going to be using for our signing, for example. In order to evaluate, we're going to compute the original PRF in the source group. We're going to take the x coordinate and multiply that by g, and that's going to be our capital Y. And I'm going to prove in zero knowledge that this is correctly computed. And the idea for proving this is to note that the challenge is proving some value of k times x. And that value we can actually break down into a number of just addition per bit of the scalar or the exponent. And once we can write that out, then you have to write that in a careful way, but you can actually write this to be a rank 1 constraint system, and then you can use bullet proofs in order to prove this. Okay, potentially you can do other things as well, but that's the way they were able to do that. By looking at this, once you break it down to the equation, the elliptic curve equation for addition, you can actually just express this as the R1CS and get a bullet proof to come out of it. Okay, this, if back of the envelope tells us 5 to 10 milliseconds, maybe it's a little bit more, but we actually have to implement this and check. So time-wise, that's actually quite reasonable. In fact, it's very reasonable. I'm looking for a nicer construction, something more intuitive, simpler. Maybe they don't exist. Maybe this is good enough and fine, and we'll implement it and we'll be happy with it. But I think that the applications are very natural. They're very strong. The constructions are, I think we should be able to find something simpler. So that's what I'm hoping that you'll all do. By the way, that eVRF is actually implicit in Music DN. Our construction is a little bit simpler, and there it's implicit in their construction. But that's what's happening. Okay, so what open questions do we have? First, we want simpler and faster constructions of eVRF. Is 10 milliseconds not good enough? Well, if it's 10 milliseconds, maybe it is good enough. We have to check. But simpler certainly is better. And for example, if we wanted to propose this as a BIP standard, as an alternative to BIP 32, I think it's probably complicated for that. We want key threshold eVRF constructions. This is the most important open question, in my opinion, because if we have such an eVRF where the pseudorandom function computed on this sum is the same as that, then we're able to get proper threshold variance for all of the applications that I said. And it's not that the pseudorandom function we have doesn't have this, it does, but everything we do afterwards, of proving the way we prove all of the proofs, these do not have this property. So that's something which we need to do as well. And I think that a fully simulatable multi-party protocol, not two-party, I should say multi-party, for ECDSA, that also has to be done. And we don't have any example of that in the literature, so that's also worthwhile doing. And if there are so many applications, there are probably more as well, so I hope that's also something that other people will find. Thank you I think that's enough given my time, so thank you very much.
So you didn't talk about this in this talk, but I looked at the paper, and it seems like the eVRF is proven using games, a game-based definition, and then the applications are proven using simulation-based. So maybe you can talk about, like, why is that not weird? As opposed to like composing. So
that's actually the standard paradigm working in cryptography. If you look at encryption, indistinguishability is a horrible definition. Why does it convince you? So yeah, what indistinguishability tells you, if I give you an encryption to M0 and to M1, you can't tell the difference. All right, but does that mean that if I'm encrypting my work contract, you can't tell if I'm earning above $100,000 or below $100,000? I mean, why is that even convincing to you? To me, it's not convincing at all. I'm convinced because another definition called semantic security, which, by the way, is a simulation-based definition. And we've proven that there's equivalence between semantic security and indistinguishability. So this is a very, very standard paradigm in cryptography. And we did that here as well. So we had a game-based definition for eVRF, because that makes it easier to prove the security of eVRF constructions. We proved that equivalent to a simulation-based definition of eVRF, because that makes it easier to prove the security of applications. And that's the best of all worlds. Having said that, having written the proofs for some of the applications, not sure it's that much easier. But the paradigm makes a lot of sense, because you can now use like an ideal functionality in proving your applications. It's nice and clean. And the game-based definition helps you to prove your constructions more efficiently.
Just a small question. How do you usually go about proving the equivalence of a game-based definition and a simulation-based definition, just in general?
So, I mean, okay, if you want full equivalence, in order to get the benefits of what I said, you just need to claim actually one direction, which is that if something is secure under the game-based, it's also secure under the simulation-based. The other direction tells you that you haven't constructed. You haven't worked too hard to construct. But you just need to prove that given something under this definition, I can prove it's secure under this, and then vice versa.
Curious about the bulletproof component that you use. Do you need succinctness from that, or succinctness is not?
No, we don't. The only thing it's a question of efficiency in interactive protocols. So it's not going onto any blockchain or anything. We don't care about succinctness.
Do you have 2-round threshold signing? Or?
Yes. We have 2-round threshold signing for 2-party ECDSA, not for multi-party ECDSA. And we have for multi-party Schnorr. In terms of threshold, it's not a perfect solution. Why? Because you need to set in advance, or you need to do like a, or you need to do this thing where you just in the first round you try for all subsets. So for a small set of parties, it's like the PVSS type construction. It blows up, so it's not very good. For deterministic, it's not true. It's not truly deterministic because if different subsets will sign, you'll get different nonces. It'll be secure. You won't have any security problems, but it won't be truly deterministic.
For DSA, the problem is the inversion.
No, we have we just didn't, I mean, the 2-party protocol.
The 2-party, that's fine.
Is easy. The multi-party just didn't do the only candidate protocol I can think of is Abi's protocol, because 3 rounds. So if you can collapse the first 2 rounds into one because you're doing nonce derivation, then it should be a 2-round protocol. But I didn't do that work. Is that the case with your protocol, Abi?
No, but you can. The first message is independent of the message.
No, that's a different thing. Once you do that, you also lose simulatability, because you need to claim that for ECDSA, it's just as secure if you get the nonce and then choose the message.
No. So the nonce doesn't get revealed in that first. So at least our proof strategy for the pipelining.
You mean that, yeah.
It's just that you start a session, you start the next session as the last message of the previous session.
Okay, maybe, but in any case, it means that your protocol is not a candidate. So it's coming out with a protocol that you can do nonce generation the first round, and then the second round. I just don't know. The protocols that I know for ECDSA are all more rounds than 3, so I don't know. But my intuition believes it should be possible, but I could be wrong. Been wrong many times in the past with intuition. So
I guess what is the if you're actually pinning the nonce, what prevents? How do you avoid the ROS style attacks?
Because you as an adversary have no freedom in choosing your nonce. You're committed to it. You're committed ahead of time.
And you're kind of turning EDDSA to your advantage.
Yeah. You're saying that if you're committed and you're using a PRF committed ahead of time, then you can now get simulatability because I know what the adversary is going to do before they actually do it. And that flips again what we said. To get simulatability, I need to be able to get the adversary's shares before I reveal the honest party's shares. And just by committing ahead of time, essentially, I'm able to do that. That's exactly what's going on here, and that gives us all of those applications.
Wait. So your intuition is that in any, let's say like an ECDSA signing, if you can basically force all of the adversaries to, for a given message, have a specific nonce contribution, then your security argument will work out? That's what you need from ECDSA?
It's a bit informal what you're saying. I also need that the honest parties are going to be pseudorandom, right? And not known to the adversary. But I need I want the adversary's shares in the nonce or shares to be, their random shares to be known to the simulator ahead of time.
So their first message, basically, it should be unpredictable but verifiable.
Yeah.
That's the trick you're using, I guess.
Essentially.
Okay. So that would make a generically then, you can take any 3-round ECDSA, have the randomness committed, and like essentially, if you just use generic
That's why I asked you, but unless you're doing other stuff. If you're doing other stuff, maybe over 3 rounds, you're starting things that you need for the consistency check. I don't know. But if you have a protocol where it's taking you 2 rounds to generate a nonce and then you're doing other stuff, then you can collapse that down. Thank you.